All right, friends, this is the most absurd server build that I have ever done. Just look at this. I have not one, not two, but three 3090 EVGA FTW3 GPUs, and they're going into my first purpose-built local AI server. And I'm bringing you along for the build. Let's get to it. Hey there, HomeLabbers, self-hosters, IT pros, and engineers. Rich here. It's finally time to build a dedicated AI server for my home lab. This is something I've been talking about building with the 2GT community now for quite some time, and after taking into account suggestions, recommendations, and leveraging connections on the GPUs, I am ready to go. And I have to say, I'm just so excited to be building a computer again. It feels like it's been too damn long. So let's get to the what, why, and how for this video. First off, why am I building this server? The primary reason is to have a bit of digital sovereignty over the expensive cloud models available today. You guys are gonna laugh at me, but I have three different AI subscriptions. One for ChatGPT, one for Claude, and of course, one for Google Gemini. I wanna be able to better leverage larger local models to remove some of the need for some of those subscriptions. Local models have gotten so good lately, especially the larger models like Gemma 4, Qwen 3.6, and so on. Right now, these local models aren't as good as a frontier model with literally billions of dollars behind them, but if they can do 60 to 80% of what the frontier models from Anthropic and OpenAI can do, that is a huge success towards my goals, and I can reduce my usage of some of those cloud models. I'm going to be splitting this project into two videos. The first video, the one you're watching right now, will focus on why I think having a local AI server is important. Then we'll move on to the hardware build, OS installation, and driver support, and finally the deployment of my AI stack. In the next video, I'll go deeper into all the different AI server components I'm using and dial them in for the best performance for my gear. So with that, let's get to it. Before we get into the parts and the build, I want to talk about digital sovereignty just for a second because I don't throw that around lightly, and it's one of the biggest reasons I'm doing this. Every one of those three subscriptions I just mentioned is a rented brain. I don't own the model, I don't own the weights, I don't own the infrastructure it runs on. I own a logon and the promise that the terms won't change tomorrow. And the terms do change. Pricing changes, rate limits change, models get depreciated or improved in ways that quietly make them worse at the thing you've been previously successfully using them for. I've seen it happen every time Anthropic releases a new, more expensive model. All of a sudden, the previous model I was using seems to get dumber. Here's the part that worries me, and I say this as someone who's using these tools almost daily. I don't think the current price is the real price. Frontier AI is being sold to us right now at a loss, subsidized by venture capital. At some point, probably when these companies go public, that subsidy will end. When it does, either the prices are going to go up, the free tier will disappear, or access will get rationed. I call this the token apocalypse. And when that time comes, these prices will go up because nobody runs a business at a loss forever. And there's a second angle here, and that's less business and more policy. These are US companies subject to US regulations, US export control decisions, and US political whims about what AI is allowed to say or do. I'm not trying to make a political video here, I'm making a resilience argument. If I depend entirely on infrastructure that I don't control for a tool I now use every day for work and personal projects, I have a single point of failure that I didn't choose and I can't negotiate with. We all saw this when the US government forced Anthropic to take down Fable 5 and Mythos 5 due to export control concerns. That really shook a lot of companies and people outside the US who suddenly lost access even if they lived in Western countries friendly to the US. And finally, the timing for this has never been better. A year or two ago, local models were noticeably behind, but that gap has closed fast. On a lot of the coding, general reasoning, and knowledge benchmarks, the best open weight models today are within single digits of the frontier closed models, and in some tasks, they're basically tied. Models like Qwen, DeepSeek, GLM, and Gemma are shipping frontier adjacent capabilities under licenses that I can actually download and run on my own hardware. And that's why I believe I can reach that 60 to 80% good enough number I mentioned at the top of the video. So, in short, I don't want my daily tools to be something that can be taken away from me, throttled, nerfed, or repriced overnight. And owning the hardware means that I own the floor. Even if it's a lower floor than GPT-5 or Claude, it's my floor and nobody can move it out from underneath me. Let's get to the hardware. All right, enough manifesto, let's talk hardware. Because I want digital sovereignty doesn't mean anything if the server I'm building can't actually run these models at a usable speed. So here's what I bought, and more importantly, here's why, starting with the GPUs. Let's start with the stars of the show, the three EVGA RTX 3090 FTW3 Ultra cards. Why the 3090 specifically when there are newer cards out there? One number. 24 gigabytes of VRAM per card. That's 72 gigs combined across all three cards. For local LLM inference, VRAM capacity is the whole ballgame. It determines how large of a model you can load and how much context you can give it before things fall over. A newer card with less VRAM is often a worse choice for this use case, no matter how much faster its compute is on paper. I owned one of these cards already, and that's why I bought two more identical used cards at roughly $1,200 each. This card launched back in 2020 with an MSRP north of $1,500. Do the math on that. A 5-year-old GPU on the used market is holding value that a normal 5-year-old GPU has no business holding. Normally, used tech depreciates. These GPUs haven't. If anything, it's firmed back up. Thanks, AI. Okay, GPUs are the flashy parts, but these next two parts are arguably the most important part of the build, the CPU and the motherboard. A normal desktop CPU gives you somewhere around 20 to 24 PCIe lanes. That's barely enough for one GPU at full speed, let alone three. So I went with the AMD Threadripper PRO 3945WX. The AMD Threadripper PRO 3945WX is a 4 GHz CPU that bursts to 4.3 GHz, has a TDP of 280 watts, and rocks 12 cores and 24 threads. 12 cores is modest for a Threadripper, but I don't need cores here, I need lanes. And this chip gives me 128 PCIe 4.0 lanes, and that means I can support all of the 16x PCIe GPU goodness going into the system. This bad boy right here was purchased off eBay for $129 with free shipping. Cooling the Threadripper PRO 3945WX took a lot of research, and in the end, I decided to use an AIO to keep that 280-watt TDP at bay with the Arctic Liquid Freezer WS360 SP6 cooler. I chose the Liquid Freezer WS360-SP6 for a few reasons. The first is that this cooler solves a problem with cooler clearance, in this case with the way the PSU stacks partially above the CPU socket. You'll see more of this when I build out the system. Also, this AIO's cooling performance is fantastic, able to easily handle the 280 watts of cooling I need without issue. Arctic makes really fantastic coolers and fans, and this low-profile cooler runs quiet, cool, and has a 6-year warranty in case something goes wrong. I'm pairing that awesome CPU with the Gigabyte MC62G40 workstation board on the WRX80 chipset I also bought off eBay for $657. This board features 6 full 16x PCIe 4.0 slots plus one 8x slot for a total of 7 slots. Every one of my 3 GPUs can run at full 16x bandwidth simultaneously. The board supports up to 8 channels of ECC and non-ECC memory, has 2 M.2 NVMe Gen 4 4x slots, dual 10GB networking via an Intel X550 AT2 chipset, a dedicated IPMI interface, a slot for M.2 Wi-Fi, 3 Slimline SAS interfaces, 4 SATA ports, built-in audio, and a partridge in a pear tree. I chose this board with help from the community because stuffing 3 EVGA 3090s into a box like this requires a board capable of having the physical space. Thank you to those who leaned in with their thoughts and input. I love our community. Thankfully for RAM, I have spare DDR4 ECC memory still lying around because the price of RAM is still bananas even for DDR4 ECC. For RAM, I'll be tossing in 8 32GB DDR4 ECC modules, maxing out all 8 channels on the board and giving me a total of 256GB of RAM per the host. This is more RAM than I should reasonably need, but if I ever overflow the GPU's VRAM, having the extra system memory means I'll be able to hold model overflow there even at the cost of speed. For storage, I'm going to toss in 2 used 500GB Samsung NVMe disks I have spare. Thankfully, I had these before the AI hardware apocalypse, because having to buy these now would have been painful. These are your typical run-of-the-mill Samsung 980 SSDs, and I intend to use one for boot, OS, and app storage, and the second one will be for dedicated model storage. Rounding out the build, a Be Quiet Dark Power Pro 12 1500-watt 80+ titanium efficiency PSU. And let me tell you, this thing is a chonker. This thing is a beast. It supports no less than 10 total 9-pin PCIe connectors, has 1500 watts of power, which should be enough to safely run the system and handle spikes in consumption, and apparently has some sort of overclocking feature, which doesn't apply here. This is the largest and heaviest ATX power supply I've ever used. There's one last thing to show you here, and that's the case. And when I tell you this was really the hardest part to find, I mean it. Finding a server chassis that's large enough for 3 full-sized 3090 GPUs was a real bitch, and there are only a few options out there, but only one, the one that I chose, actually was able to fit all this gear and wasn't a purpose-built server chassis. Ladies and gentlemen, I give you the Rosewill RSV AI01. This is my first experience with Rosewill, and to be honest, I thought Rosewill made crappy gear, but I was wrong. Every inch of this 4U chassis is premium and well built. It features 8 hot-swappable SAS connectors up front, 11 total expansion slots, fits up to an extended ATX SEB motherboard, features 3 hot-swappable 120mm fans in the middle of the chassis, 2 80mm rear extraction fans that can help you pull hot air out through the rear GPUs for better cooling, has USB-A and USB-C connectors in the front, and comes with rack rails by default. Now, if it only came with the white bezel. But hey, nothing a little white rattle can can't fix at a later date. The only downside here is that this case wasn't cheap at $500 shipped to my door. And a budget note. Total spend on this platform is not cheap. Doing the math here, not counting the items that I already have on hand, I spent roughly $3,635.53 on parts. That is not a humble brag. If I didn't have the first 39 GPU, RAM, and NVMe SSDs, I estimate the actual total to be somewhere north of $6,000. So, if your goal here is the cheapest possible way to run a 7 billion parameter model, this is the wrong video for you. This is a run genuinely large models at a size that can meaningfully replace Frontier subscriptions, and that costs real money, even buying used as I did. So, with that out of the way, let's build this beast. The build process went painlessly. The first step was to prep the motherboard for installation. That meant tossing in the Threadripper CPU, the 256GB of RAM, the 2 500GB Samsung NVMe drives, and then of course, mounting the board and everything into the case. Next step was to figure out the best way to mount the AIO cooler into the case. Fortunately, only one way made sense, and that was with the tubing exiting on the far right side of the case. Once the radiator was mounted, it was time to lube up the Threadripper with some Arctic MX6 thermal paste, and then attach the water block to the processor. Next came the fun of connecting the front panel connections, or rainbow wires as we used to call them back in the day. I had to pull out the online manual for this one, but everything went quickly and smoothly. Now it was time to stuff in the 3 3090 GPUs. The first and second GPUs went in without much fuss, but the final third 3090 was more difficult due to the tubing from the AIO on the right. With the help of my friend John and some patience, we were able to get all 3 stuffed in there. Finally, power was last. There is a significant amount of cabling going into this box. All total, there are 9 8-pin PCIe connections for the GPUs, 2 8-pin CPU aux connections, the 24-pin ATX power connection, and I did run power to the front disk array just for future-proofing. Looking at the end results here, there is no way this server could have used an air cooler in this box under the PSU. There just wasn't enough headroom, and on top of that, with the massive amount of cable stuffed in there, I'm thankful I had an AIO. And the final results speak for themselves. Everything came together and looks great. With those 3 3090s in there, that is a whole lot of heatsink in one box right there. Now it's time to move on to the software install for this system. Our first step here is to get Ubuntu Server 2604 installed. To do this, we'll be using the AMI MegaRack management interface built into this board. Let's get to it. I'm gonna run through this quickly. I'm booting off a USB stick that I've written the ISO to using Rufus. There's nothing special about the installation process here for Ubuntu Server. We're gonna stick with the defaults and get the OS installed. We'll select my language, test the mirrors, format the OS disk to my liking, set the first user, and kick off the installation of the OS. Start to finish, it probably took around 7 to 10 minutes. From now on, I'll be SSH'd into the host because it makes it dramatically easier to interact with the console since I can copy and paste as needed. The first thing I always do is fully update the host after a fresh install to prepare it for the next steps. I'm a big fan of compounding my commands when I'm able to do so. I'll be using apt update, -- apt dist upgrade -y, -- apt auto remove -y, -- apt auto clean -y, and finally reboot. This single command updates, upgrades, cleans up, purges, and reboots the system. Easy peasy. Arguably the most important step of the setup process is next, and that's getting the Nvidia drivers installed properly to work on our system. This used to be a huge pain in the ass back in the day, but thankfully it's not anymore. It's quickly solved with just a few commands. First command I use is ubuntu-drivers space devices. This command shows me the available drivers for the hardware that's in my system, specifically the Nvidia GPUs. There's a big list here of different driver options to choose from. Because this is a server and it doesn't run a GUI, we'll be installing the Dash server variant here. You can choose any variant you'd like here. I'm going to go with Nvidia driver 595 server for this build. I'm going with this version of the driver because it's not the newest of the new, but it's also not the near end of life version either. To install it, we'll type in apt install Nvidia driver 595 server, and hit enter. There are a ton of packages that will be installed as part of this, including a kernel recompile for the new driver as well. We'll hit Y to kick this off. Once that's done, we'll reboot the box using the command reboot. The final step after the host comes back is to validate the drivers are properly installed and that we can see the GPUs. And to do that, we use a tool from Nvidia that was installed as part of the previous process called Nvidia SMI. So we'll type in Nvidia-SMI and press enter. Nvidia SMI shows you all of the Nvidia devices available in the system, including their usage, thermals, memory consumption, and what processes are using them, if any. I can see all three of our Nvidia 3090 GPUs listed here, all happy and ready to go. Okay, we're about finished with the installation process here. We have two core components left to install, Docker CE to run our containers, and the Nvidia Container Runtime to allow Docker containers to access the GPUs directly. Here's the thing, there are a lot of steps here to show, so here's what I'm going to do. Go to our website, the URL is right here, and there you can find the exact text to paste in if you're playing the home game and following along here. I promise you this is not a gimmick to get you to visit our website. It really is the easiest way to share these blocks of text because doing so in a video would be a huge pain in the butt. Let's get this stuff installed. Alright, we'll paste in the Docker install text and hit enter to install. This will clean up any previous Docker installs if you have one, add the Docker CE repository to your host, and install Docker, Docker Compose, and any other necessary supporting software. Once it's complete, we'll check to make sure Docker is running by typing the command docker ps and hitting enter. Just getting back any information tells me that Docker is working, which is great. Next is the Nvidia Container Toolkit support I mentioned a bit ago. Again, this is a giant block of text, so copy this from the blog post on our website, paste it in here, and hit enter. This command adds Nvidia's trusted key to your system, adds the Nvidia repo to app to download and install the runtime, installs the Nvidia Container Toolkit and supporting packages, and restarts Docker. Once that's done, we've added all of the foundational configurations we need to start running AI workloads. Let's talk about that now. Let's quickly talk about why I'm using Docker in my AI stack. For me, containers are the best method for deployment for AI services for a few reasons. One, they're incredibly easy to update with no risk to the underlying operating system if something goes wrong. Two, a lot of the base configurations of these applications can be configured as part of the Docker Compose file, which means my setup is very portable and I can install it pretty much anywhere. And three, this is how the industry does it. Obviously, bigger cloud installations are using Kubernetes over Docker proper, but for a single host setup, Docker is the way. I'm going to run this now just to show you it's spun up. My entire Compose file is available on the site as well, and in the next video, I'll go into depth about each of its components, its configuration, and why I chose to do it this way. I just can't stuff all of this into a single video. Let's get to it. This Docker Compose file will build out a container of Ollama, WebUI, Tika, Qdrant, SearchXNG, and OpenTerminal and connect them all together in one simple deployment. It's an incredibly simple and convenient way to deploy everything quickly and easily. We'll talk more about this in depth in the next video. With one single command, Docker Compose up -d --build, everything gets downloaded, spun up, and is ready. You really can't beat the ease of Docker Compose. I love it. So let's get to the final thoughts here. First off, again, super happy with that Rosewell case. I'm honestly not sure where I got the negative feels about them in the past, but this case is pretty superb. It would make a fantastic server case even if stuffing it with GPUs isn't your primary objective. 8 hot swap SAS bays up front, 4 internal mounts for 2.5 drives as well, hot swap fans, room for a radiator, and the build quality is fantastic. Only downside is that you're probably going to have to commit to an AIO if you go with this case just due to the PSU's shelf location. One more thing to add here, the build went easy, but I did run into an issue with the fan headers on the motherboard. Gigabyte puts all the case fan headers on the right side of the board, which is fine, but when I put that final 3090 into the final slot, those fan headers with fans connected wouldn't allow the GPU to fully seat into the slot. Kind of a niche case here, I know, but something you should be aware of if you're going the same route I did. Finally, I know I skipped over the AI stack deployment portion of this video, and that's on purpose. There is a lot going on with the compose file I'm using, the different containers, and their functions, and I really want to have a dedicated video to discuss how all of that works because it's complicated. The hardware is really separate from that portion. That video will be out soon, so keep an eye out, and in the meantime, check our website. I've posted all of the commands, the compose file, and further details on how this is built. Thanks for watching this video, folks, and thank you to the fine people you see here who support us through Patreon and the YouTube membership program. If you'd like to support what we do here, consider checking those out. Join our community Discord and chat with me and like-minded home labbers, geeks, and nerds. And as always, we'll see you on the next one. Thanks for watching.